Hi, Mitu. Hi, can you hear me? Hi, Mitu. Can you hear me? Can you
You
please respond?
yes, I can hear you clearly.
Yeah, yeah. So we are waiting for 5 or 10 minutes, then so that everyone can join. Mitu, can you confirm, is my screen visible?
Yes, I can see the first page of the presentation.
Yeah, yeah. Thanks.
Hello, hello.
Ha. Yes, yes, Mitu.
Yes, sir. Like we have in this assignment, we will have numericals based on the first module in the exam also.
Mm-hmm. Mm-hmm.
Okay. Okay. So we use all the formulas which we have derived for the mechanical expressions for all the beams.
Yeah.
So it has to be applied in the numerical form to get the
Yes.
results.
Yes.
So do
Yeah. Yeah.
sensors are also planned like that? Means mechanical problem is implemented onto a scale, so small scale on the wafer.
Yeah. So
When we
there are
plan to
different
make
type
the
of
sensor.
yeah. So there are different type of sensor actually, and in this
Okay.
course we are basically concerned about mechanical, electromechanical based sensor. So the first module is basically we are revising the concept of basic mechanics,
Okay.
and these basic mechanics. So basically these are piezo resistive sensors. So we
Okay.
apply some piezo-resistive sensor in these beams, and we apply the
Okay.
force, and we get some what we call sensitivity. And after getting these change in basically electrical parameters like threshold voltage, we measure the
Mhm.
sensitivity.
So do all sensors have the silicon base? The bulk is on they are
No, no,
designed on the silicon base. Okay.
no. It's not the case.
Okay. Any material which
Yeah,
base material could be made and beam is grown over it. A cantilever basically is grown over it, and then the
true.
it senses whatever the means. Piezo means your pressure and deflection.
Yeah.
Okay.
Okay, so I think many of them have joined, so we can start our discussion. So I am Nalin Vilochan Mishra. I am from Department of Electrical Engineering and Computer Science, IISER Bhopal. I am PMRF fellow here, and I'm one of the TAs for this course, a brief introduction of microsensors. It is taken by Dr. Shantanu. He is I think, assistant professor in IISER Bhopal. Okay, so let us start with week one, which is basically numericals. I'll cover numericals on basic mechanics. Okay, so starting with a very basic formula of stress. I think all are familiar with this formula: force upon area. This can be written as sigma, force upon area, and strain. It's given by change in length upon length. It is given by sigma. We also know the Young's modulus constant, which is given by Y or E, which is basically stress upon strain. So we can write like Y equal to sigma upon E. So I have this first numerical for you guys, a very simple one to start with. I'm writing the question here. So cylindrical silicon rod is pulled on both ends with a force of 10 millinewton. The rod is 1 mm long and diameter is 100 micrometer. So what you need to do, find stress and strain if the force is applied in longitudinal direction. In longitudinal direction. Uh, the Young's modulus is given as 130 gigapascal. I hope the question is clear. It's pretty simple. It is based on these two formulas, stress and strain. Please try it. If anyone has any doubt in the question, please uh, turn on your mics and ask me. So I hope everyone has already seen these three lectures given by Dr. Shantanu. You can type in the chat box. I'll read it. Has anyone solved it?
Is the answer is 1.27 megapascal?
For what you are answering, stress or strain?
Stress, stress.
No.
Hmm?
So the diameter is given, not radius, and you need to first calculate the area. So I hope you have correctly
That
calculated
would be
the.
that would be cross sectional area only.
Yeah, that would be pi d by 2 square. Has anyone else solved it? So I can see four people or five people. So 40 people joined right now. I'm repeating. So it's a very simple question. A cylindrical silicon rod is pulled on both ends with a force of 10 millinewton. The length of rod is given as 1 millimeter and diameter is given as 100 micrometer. So you need to find stress and strain. The formula for stress is force upon area. and for strain is it is change in length by L, or the formula for Young's modulus is stress upon strain. So strain can be given as stress upon this coefficient. So this coefficient of elasticity. Mitu, so you got the answer?
Sir, I got 1.273 into 10 raised by 6 Newton per meter square as stress.
Okay, so what I have is 3.18 into 10 power 5 Newton per meter square. Maybe some mistaken unit. Okay, so let me do it. So stress is given as force upon area. The force in the question is given as 10 millinewton, and area we can write it like pi r square, which is basically d by 2 square. So it will be 10 millinewton upon pi. Diameter is 100, so we can write 5 micrometer whole square. And answer what I have in here is 3.18 into 10 power 5 Newton per meter square. Strain can be written as stress upon this coefficient. So it will be 3.18 to 10 power 5 by 130 gigapascal, and it is coming out to be, let me calculate it, 0.02 into 10 power 5. This is giga. Has someone solved it for strain? How much it is coming?
It's 2.44 micrometer. No, no unit,
2.4,
no unit. 2 micro
2.4. Okay,
into 10 raised by minus 6.
into 10 to the power minus 6. Okay, so for strain I don't have, so maybe I hope it's correct. Okay, so this is the very basic formula, which is but very basic but very useful in these beam calculations. Uh, so let me revise you some of the concepts of basic cantilever beam. So the case one, a basic cantilever beam. So assume a cantilever beam with width of this beam equals to W. The length of this beam is given as L, and the force we are applying in axial direction F, and the force is F, which is applied axially. So in this case, the stress will be force upon area also assume the height, so basically the thickness of this beam to be h. So the area will be W times h. And what is strain? Strain is basically the change in length upon the total length. It is given by epsilon. So basically what will happen if we apply the force? So when we apply the force in this direction, the length of this beam will increase, and it is given by delta L, and hence we are saying sigma is change in length upon total length L. Also we know that Young's modulus or E is given by stress upon strain. So we can write stress as force upon area and strain as change in length upon total length. So force can be written as WH multiplied by Y, also change in length upon L. From this basic spring mass system, we know that F is directly proportional to the deflection of this mass, and which is given by F equal to Kx, where this K is called stiffness constant. Here, if we compare this equation 1 and equation 2, then we know this constant Kx, we can say, because we are applying force in this x direction. So it will be WH, which is basically area, Young's modulus, by total length. Anyone has any issue till now? I think it's very basic. No? Okay. So case 2, what happened when we apply the force? Case 2, what happened if we apply the force in this transverse direction? So let us consider this beam with length L, width W, thickness H, and we are applying force in this transverse direction. So after applying this force, the beam will tend to bend, and we need to calculate this deflection x or del L. So for that, uh, deflection in this x direction is given as FL to Young's modulus y, moment of inertia I, multiply with x square 1 minus x by 3l. So this formula is derived for pure bending case, and I'm not deriving this formula. You can check I think lecture 1 or lecture 2 of Dr. Shantanu. He has derived it. Here I is moment of inertia, and x is basically the position in x direction. So if we are calculating the force at the tip, so we can say x here is equals to L, and we put this in this equation of uh, Wx. So it will be and it will be equal to FL cube by 3yi. So this relation is you can memorize this relation, and the force is basically 3yi multiplied by this W by L cube. We know the proportionality constant F is force is directly proportional to this deflection W. So the coefficient of so basically stiffness coefficient KT is equal to 3yi by L cube. So in previous case we derived this relation Kx. So Kx is the stiffness constant if we apply the force in x direction, and Kt is the stiffness constant if we apply the force in transverse direction. So these are the two cases. So based on this, I'm giving you one more numerical. Let us try this. So find the stiffness coefficient, or we can call it force constant, for this figure. So we have already derived the stiffness coefficient for this case, I want you to derive the stiffness constant for this case. I am applying force in this direction, not from the top, but from the side. So it's not the axial force, it's not the transverse force, but I am applying a force perpendicular to the thickness T. So please try. And so it's also a very simple thing if you think about it. Before that, let us revise about moment of inertia. So I hope you know about this formula. So if there is this cantilever beam which is fixed from this end, which has the width of W and thickness of T, and if we are applying the force from top, so basically what we are doing, we are applying the force perpendicular to the width W, and if we are applying the force perpendicular to the width W, then moment of inertia is given as Wt cube by 12. Use this and you can try this numerical. The width of this beam is given as W. Please try.
But sir, in left figure, F is perpendicular to W, but in the right figure, F is parallel to W.
Yeah. So this is the only thing which is different from this figure. So this is the
So
general case. Yeah.
then the moment of inertia will be different for the figure right side.
Yeah. You need to calculate that and
Okay.
accordingly calculate the value of stiffness constant. So can anyone tell me what's the formula for stiffness constant when we apply the force in transverse direction? So is this the case of applying force in transverse direction? The beam is basically anchored in with this wall, and we are applying force in this direction, which is force is being applied perpendicular to the thickness T. So can we apply this uh, stiffness constant formula 3yi by L cube here?
Yes, sir, we can apply the same formula, but I would be different here. I would be
Yeah.
now TW cube by 12.
What it should be? T.
It should TW cube by 12.
Yeah, that is true. So we put this I in this formula. So it will be 3y T W cube by 12 L cube. So K would be y T W cube by 4 L cube. Everyone is getting this answer? Other participants, Rajani, Shubham, Smita, and Vidyashri, are you also getting the same formula? Okay. Mitu, is the last numerical was clear to you, no?
So you mean the stress strain one?
This one.
This
This,
one?
yeah,
Bending case. Yes, sir.
yeah, okay. So
Okay.
now we will revise the case of beams in combination, series combination and parallel combination. So let us assume this spring mass system where two springs are connected like this with a common mass body M, and the force we are applying in the transverse direction. The constant for spring 1 is given as K1, and the deflection for spring 1 is given as X1. Likewise, K2 for spring 2, and X2 is the deflection for spring 2. Tell me what will be the same if we apply a common force F. So the deflection should be same for both spring or the force.
Sir, deflection. No. Yes, deflection.
Okay. Yeah. So basically, this is a parallel case. Here, springs are connected in parallel combination. If we apply a force downwards, both spring will move together and deflection x would be the same. So we know F equivalent is F1 plus F2. It can be written as K1x plus K2x. Since x are same, so K equivalent equal to K1 plus K2. For series, consider two springs connected in series with a mass m, and we are applying a force. The spring constant for spring 1 is K1, and it is having a deflection x1. K2 for spring 2, x2 is the deflection for spring 2. In this case, what should happen? Can deflection be different in this case, or it should be same?
The force is same, deflection is different.
Yeah, so in series connection, deflection would be different. So we can write like x equal to x1 plus x2. This will be equal to force by k1 plus force by k2. Since force is same, for series combination, k equivalent can be written as 1 by k1 plus 1 by k2. Has anyone any doubt? No? Okay. So another example. So assume there are two beams of same length but different cross section. A1 and A2. These two beams are connected with a mass m, which is given as 50 milligrams, which is accelerated with acceleration 9.8 meter per second square. So what you need to do, you need to find equivalent stiffness constant. So let me draw. There is this two beams. These are connected with a common mass m. This mass is accelerated in x direction you need to calculate the stiffness constant. Please give it a try. Here values are given. A1 is equals to 4 mm square, A2 25 mm square, and Young's modulus is given as 150 gigapascal, and length is given as 100 millimeter. I think this is all you require. So can anyone tell these two beams are connected in series or parallel?
Parallel.
Yeah. Rajani, you have raised your hand. Is there any doubt? So since these two beams are connected in parallel, we can write K equivalent as K1 plus K2. So what is the stiffness coefficient if we apply the force in this x direction? If we apply the force axially, I think it is YA by L, if I'm not wrong. So for K1, it is YA1 by L, and for K2, it will be YA2 by L, since the length are same. So K equivalent will be K1 plus K2, which is equals to Y by L A1 plus A2. Numerically, you can calculate it later. The second case, case 2, these two beams with same length cross section given by A1 and A2 are connected in this fashion. Here also the mass is accelerated in this x direction. Here, can anyone tell me how these two beams are connected? It's in series or parallel?
So again, parallel.
Yeah. How can you say that?
Because when the mass will be moving, the
Mhm.
displacement will be same for both the beams.
Yeah. So yeah, correct. So because the deflection is same, hence these two beams are connected in parallel. So here, what would happen when we apply the force? So the mass will move like this. So there will be the deflection delta L in this direction and in also in this direction for this beam, but for this beam it will be minus delta L, and for this beam it will be plus delta L, but the deflection is same, and hence these two beams are in parallel. For parallel connection we already know K equivalent is K1 plus K2, and it will be the same. K equivalent will be Y by L A1 plus A2.
So what
Third
is the
case,
answer numerically?
numerically, I think I don't have it now, but
Okay.
it's the same. It's simple formula. I guess you can calculate it. How much you are getting?
Sir, I got it 4.3 into 10 raised to 7 Newton meter.
4 point.
4.3
Okay, I'll
into
check.
10 raised to 7 Newton meter.
Okay, I don't have it right now, but I can check it. Okay, so the third case, it's the simple. For this case, let me know the answer. So it's connected in series or parallel? This is the case of series connection, as both beams are experiencing the same force, right? So it will be K1 is equals to A1 Y by L, and K2 is A2 Y by L, and K equivalent is given by K1 K2 by K1 plus K2. In this case, delta x is, I have the numerical answer for it, 0.0948 nanometer.
we have to calculate the delta x for both cases or k equivalent for both cases.
You can calculate it in both ways. You can calculate it by k1, k2, then x1, x2, or you can calculate first the k equivalent. Then you can apply this formula f equal to k equivalent, x equivalent, and then you can finally get this. If in your exam they are asking x1 and x2 both, then you need to calculate by that way. It's clear? Should we move to case 4? Okay. Here, thickness of this beam is, so there are two beams connected in this fashion. The thickness are same T, length is also same L, and width is also same W. We are applying force in this transverse direction. Force is F. So we are applying force in transverse direction Fy. So for this case, this is a series combination or parallel? What would be the same, deflection or force? Parallel, yeah, true. So if I make spring mass system for this case, it will be like this. Spring 1, spring 2, both are connected with a common mass, we can assume it, and we are applying a force in bidirection, which is a transverse force. Do we know stiffness constant for this case? This one. So it is given by 3yi by L cube, and we know that for parallel case we can directly add the stiffness constants. So K equivalent will be 2 times 3yi by L cube. Okay, I have one question. What will be this I? Please unmute and answer this. What should be this I? W is this in plane width, and thickness is this, we can say, in this y direction. What should be I?
So then it will be force will be perpendicular to W only. So I will be
Mm-hmm.
W T cube by 12.
So I should be W T cube by 12, right?
Yes.
Yeah. So KT will be 3y. We can write W T cube by 12 L cube. It will be y by 4 L cube W T cube. Everyone got this case? Okay, next question. So two cantilever beams of same length and material, one with cross section W cross H and other with cross section W by 2 cross 2 times H. So the question is, which beam is more resistive, beam 1 or beam 2? So the width is this and height is this thickness of this beam. So for one beam it's W and H. For other beam it's like this, W by 2 and 2 times H. Beam 1 and beam 2.
So both are subjected to axial force or transverse force.
Hmm. Uh, so you can assume both are. I think you can assume axial force in both the cases. Or do one thing, assume transverse force. Assume transfer force in both beams.
The stiffness constant is greater for beam 2,
The stiffness constant is greater
uh,
for
for beam 2.
beam 2. Okay.
So
And
it will be more resistive.
yeah, so if stiffness constant is more stiffer, you can say it's more resistive for any type of force.
But in transfer case, because both,
Yeah.
as your voice is breaking, am I able to hear like that or?
No, no, I think if this is the case, my internet has some issue. Is it correct now?
Now it's okay.
Okay.
But sir, in actual case, because cross-sectional area
Mm-hmm.
would be same for both, so then both
Yeah.
will be equally resistive,
Ah,
right?
yeah. So if for axial case, it will be same because the area would be same. That's why I told to calculate it for this transverse direction. So how would you calculate it?
Sir, I
You first need
calculate
to yeah.
because stiffness constant K is equal to 3yi by L cube. So
Mm-hmm.
stiffness constant is proportional to inertia, moment of inertia I. So since
True.
transfer case, its force is perpendicular to W. So for first
Mm,
case, now the stiffness constant will be W h cube by 12 for case 1. For case
mm,
2, now W is W by 2 and H is 2H. So for
yeah.
this case, stiffness constant is WH cube by 3. So
True.
hence K2 greater than K1. So beam
Hmm.
2 is more resistive for transfer
Yeah.
case.
Yeah. Correct. Correct. So the stiffness constant is basically equal to 3 EI by L cube. So K is directly proportional to I. So first we need to calculate I. So I is given as WH cube by 12. So after calculating, I2 would be 4 times of I1, and hence K2 is greater than K1. So answer is K2. K2 will be more stiffer and hence more resistive. Okay. Also keep in mind K is also directly proportional to E, and K is also inversely proportional to L cube. So you may get these type of questions also. Also, if the force is applied in this direction, so what would change? So for this case, moment of inertia will change. It will be h w cube by 12, right? So let us move to another question. Guided beam case. So what is guided beam? Guided beam is also similar to cantilever beam, but it is here connected. So it cannot move in this x direction, and it also cannot rotate. So only transverse motion is allowed. Okay, and in this case you can calculate the stiffness constant is 12 yi by L cube. The derivation is already shown in the main lecture videos. You can go and see that. Okay, so another question. So there is this proof mass. It has mass m. It is connected with two beams like this, and these are anchored here. The length and cross section are same for all the beams. The direction is like this. This is x direction, this is y direction. So for this system, find the deflection if case 1 an axial acceleration ax acts, case 2 transverse acceleration ay acts, case C uh, if acceleration is applied at 45 degree from x-axis like this. So let me repeat the question. Assume a micromechanical accelerometer with a mass m with four suspension beams and anchor are connected like this. So find the deflection for three cases. First, if axial force is given ax, this is case 1. Case 2, if transverse acceleration is given like this, and case 3, if the acceleration is applied at an angle of 45 degree. So these four beams are connected in parallel or series or some combination of it. It's like all parallel or series or two in parallel then series. How these are connected? So for that, first we need to draw the spring mass system or free body diagram. So first we need to draw free body diagram. These all are connected with an anchor. So these two and these two are connected in parallel or series.
Parallel.
Yeah, like this. Now
Again parallel.
again parallel. So let us assume the constant k. It is same for all the beams. Now it will be 2k, and finally it will be 4k. So k equivalent is 4k. Now for the first case, we are applying the force in x-axis like this. So what is the formula for stiffness coefficient?
Sir, EA by L.
It will be YA by L. So K equivalent will be 4 YA by L. Then how can we calculate the deflection? We know that force is equals to K equivalent multiply with deflection. So the force divided by K equivalent would be equal to the deflection. So it will be everyone getting the same answer. Deflection equal to FL by 4 by A. This is case 1. Case 2. So what is case 2? Case 2 is we are applying the force in this y direction. And it's a guided beam. So for guided beam, we know that stiffness constant is equals to 12 by I by L cube. And K equivalent will be same as previous case. All 4 beams connected in parallel. So F equal to K equivalent multiplied by deflection. So deflection will be F by K equivalent by 48 YI by L cube. Correct? Now what about the third case? If an acceleration is applied at an angle of 45 degree, what will happen then? In that case, K equivalent is basically resultant of axial coefficient of stiffness and transverse coefficient of stiffness. Okay. Next question.
So for this means Kx, the Kx would be the 4K which we calculated for case 1.
Mm-hmm.
For the third case, if we have calculated the K equivalent, then Fx is Al, Fx is Ya by L, and Ky would be 12
Yeah.
Yi by L cube.
Yes, this kx we have already calculated for case 1,
Case 1,
and this ky we have calculated for case 2.
2. They are basically the results of first and second 4K basically.
True.
True. So then this K equivalent will not be needed to be multiplied by 4 because they are
No,
all, the 4 factor is already incorporated in Kx and Ky.
Yeah, so this will be the final formula for the third case.
Okay, sir. Okay.
Now consider this system. The four beams. Uh, so let me tell you the question. Consider the suspension system for a square mass as shown. It consists of four beams which is connected with mass m and anchored at the end. The dimension length of the beam is L, width W, and thickness T. So you need to find the stiffness of the system. The direction are X, Y, and Z. So for this case, I think assume thickness also W. So it's the square beam. Width and thickness both are W. Length is L. Width and thickness are W. So how many forces we can apply for this system? We can apply one axial force in this x direction. We can apply transverse force in y direction, and we can apply this force which is basically out of plane in this z direction. So first we need to calculate the stiffness constant for x direction, then we need to calculate it for y direction, and then for z direction. Also, you may notice this suspension system is basically symmetrical in nature. So if you calculate it for basically, if you assume, sorry, if you assume this beam 1, 2, 3, and 4. So if you calculate the axial force for 1 and 2, it will be same as transverse force for 3 and 4. So only one case is needed for calculating. So as I was saying, if we apply axial force AX in x direction, stiffness coefficient we know YA by L, it will be same for 1 and 2. And for 3 and 4, it is a case of guided beam. So we know the coefficient, stiffness coefficient is equals to 12yi by L cube. So since deflection is same in all directions, hence we can say K equivalent is equals to K1 plus K2 plus K3 plus K4. All beams are in parallel. So K1 and K2 were by A by L, and K3 and K4 were 12 by I by L cube. So K equivalent for X case, because we have applied force in X direction, it will be 2 A by L plus 24 yi by L cube. And what about deflection? Deflection can be calculated as F by K equivalent. So we notice the symmetry in x and y direction. Hence, we can say, since there is symmetry in x and y direction, hence wx is equals to wy. Also, k equivalent x is equals to k equivalent y. Now, what about the third case? Kz. For that, you need to imagine a force Fz in z direction, like this. Like this is x, y, and z. So the force is applying. We are applying a force in out of the plane direction. So can we say uh, it's also a guided beam case with transverse force? It's also the same, and k equivalent will be 4k because the deflection felt by all beam would be same. So W equivalent for Z will be F times K equivalent for Z. Correct? Here you need to try for this second case. You can try it in your home. Consider the thickness T instead of W and see if something changes. So guys, have you solved the assignment questions?
Yes.
You have solved it.
Yeah.
Okay.
So, but the confusion comes with the proof mass questions.
Proof mass question. Okay, so I have one question. I think the same question which Shantanu sir had told in the class. Let me show. It is something like this. These two beams are anchored, and it is connected to this proof mass. So there are four beams. These four and these four. Assume the length L for all the beams. So if the force Fy is applied, so basically we are applying a transverse force, then you need to calculate the stiffness coefficient, stiffness coefficient and deflection. So for that, first you need to make free body diagram. Here assume this proof mass which is accelerated with force F. Now think of this beam. Let me name it beam B. Assume this point as B1 and this point as B2. So if we move this proof mass system by 5 micrometer, then this B1 will also move 5 micrometer, but this B2 will bend. So this beam will bend and B2 will move. So if B1 moved 5 micrometer, so B2 will move less than 5 micrometer, because these uh, are connected. So these beams are fixed and hence it will not move by 5 micrometer. So let me as A, C and D. So this point is A2, this point is A1. Likewise, this point is C1, this is C2, D2 and D1. So B1 is directly connected with proof mass. We can draw as a spring for beam B. This point is B1 which is connected to proof mass. This is point B2 which is directly connected with beam A. Now this B2 and A2 are directly connected and A1 is anchored. Same goes for beam D. B1 is connected with proof mass and D2 is connected with this beam C. This we have done for left hand side. We can do the same thing for right hand side also. Let me name it E F G H. So this is E F and this is H and G. So for this system, K equivalent will be, so this beam B and A are connected in series, so it will be K by 2, assuming the stiffness constant is same for all the beams, and this for CD is also K by 2, and stiffness constant AB and CD are connected in parallel, so we can add them. So K equivalent for ABCD will be K. Similarly, K equivalent for EFGH is also K. Now, so till now we have this proof mass and two spring mass system which are anchored like this. This is K ABCD. This is K E F G H. Now we know that okay, so these two spring mass system also, so these two springs are also connected in parallel. So K equivalent is equals to K ABCD plus K EFGH, and because they are equal, so we can write K equivalent equal to 2K. And what about K? What is K here? For guided beam, it is 12 by I by L cube. So K equivalent is 24 yi by L cube. Any doubt for this question?
Sir, in the proof mass diagram, the force mass diagram, sir, where have you mentioned the beam A, B, C, D? So that is okay how they are anchored. But while visualizing it, can you just highlight which is the beam exactly? Suppose the A beam, it's the empty space between the two lines, or the hard mass which is extended,
No,
that
no,
is beam.
no. Okay. So
If you can highlight the
yeah,
beams like B beam, A beam, how could it
so
be?
yeah, so actually, let me.
That I can understand, like one is fixed to the proof mass, one end is fixed to the proof mass, how is it anchored? But the beam exactly, which is one is the beam,
Yeah,
that is hard to visualize for me. For me, I don't know for the others, but am all I was also confused while the lecture also now also.
okay. So this is the beam actually, if you can see. So this beam, let me draw another diagram for you. So I'm only drawing this A beam. So this is the beam and this is connected with this anchor, or it is fixed so that it cannot move. So this is the A beam. This is point A2. This is point A1. And another beam is like this. It is also anchored here. This is C beam, C2 and C1. And this space, which is the blank space actually. This this is the blank space.
Okay. Okay, sir.
I hope it's clear now.
Yes, sir. Now, sir, if we consider B and D that are over the proof mass, that is the
Yeah,
extension of the proof mass, B and
true.
D. Okay.
True. So this BND is basically, we can say, it's a part of proof mass because it is directly connected with proof mass. And these A and C are like two fingers which are coming out with this mass, and these two fingertips are anchored. So this you can assume these two fingers as the beams, and this free space is this highlighted portion.
Sir, if we can see it's in a transverse way, so the proof mass with the lower portion of the layer, and on over the top of it, some extensions would be there like A and C. If we see the transverse section,
Transverse section. You are talking
transverse
about.
section, like this is a overhead view, this
Mm-hmm.
proof mass and this thing. If we see a side view, so this would
Uh,
be a layered structure, a proof mass base, and then over it some extensions for A and
so
C.
so you should visualize like this. So this is the beam, and the proof mass is like this.
Okay.
So we are so this diagram is basically we are seeing from the top view.
Okay.
है ना? So this is the top view, and assume like my hand. This is the proof mass, and we are pushing the proof mass like this in the
Okay.
y direction. So when we push the proof mass in this direction, along with the proof mass, the point B1, D1, and this E1
E and H.
and H1, not E and H, the point E1 and H1, because
Okay.
of this anchored masses which is connected with the beam A, C, F, and G.
Mm-hmm.
The this vertical section, this vertical beam will also bend. So that's
True.
why B1, D1, H1, and E1, this will move with the proof mass, but it's not the case for point B2, D2, E2, and H2.
Done. Okay.
I hope I'm able to make you understand.
I can only visualize it if there's a two structures. Like if you say one your hand and over above that hand two beams A and D are protruding on some other.
Hmm. So what we can do for this, in the next tutorial session, I will make some model out of it, and I will try to show you the 3D model so that you guys can visualize.
Okay, sir. That will be quite helpful.
Yeah, so in the next
Okay.
class, I will try to show you that.
And sir, one more thing, sir. Any book for the reference?
Yeah, so for book, I will tell you. So there is this one very good book, G. Ananta Suresh. Let me also give you the publisher name so that you can find. Wait a second. So the title of this book is Micro and Smart System by G. K. Ananta Suresh. Other book would be Micro System Design by Stephen D. Centuria. It is the publisher is Springer. So these two big books you can refer.
Okay.
And for the other doubts, you can mail me at nalin20@iserb.ac.in. If you guys have any doubt or any query, you can mail me in this ID. Okay. I will send you the recordings and the material. I think my laptop batteries is drained. Okay, so this is for today's session. We will meet on next Saturday, 3 to 5. I hope the session was helpful for you. Okay, so bye guys. We'll see you in the next class.
जो हम एक गेम डाउनलोड हो गई थी. Okay, sir. Thanks a lot. Thank you for the session.
Sure.